Hello, welcome to Chapter C on Galaxies, Part 2, Galaxies Across the Universe. In this second part of our chapter on galaxies, we'll be looking at the huge selection and assortment of galaxies that exist in our universe. Just a quick review. A galaxy is a huge star system containing up to several hundred billion stars. Let's start out with our nearest neighboring galaxy, the Andromeda Galaxy, which is also called M31. This galaxy is actually visible to the naked eye. If you know where to look in the sky on a really dark night in the fall or late summer, you can see a little faint fuzzy spot in the sky, and this is actually the Andromeda Galaxy. This is a neighboring galaxy to our own Milky Way galaxy. It contains approximately 400 billion stars. The size of this galaxy, like all large spiral galaxies, is immense. It's approximately 100,000 light years across. Remember that a light year is approximately 6 trillion miles. The distance from Earth to this galaxy is estimated to be about 2.5 million light years. Now think about what that means. Light took 2.5 million years to reach the Earth. So even though I took this picture through my telescope and with a camera fairly recently, this is not a recent picture of the galaxy by any means. This is what the galaxy looked like 2.5 million years ago. So this reminds us that telescopes are like time machines. The farther we look out into space, the farther back in time we see. There are so many galaxies in the known universe that it at first seems like an overwhelming or even futile task to try to make sense of them all. But as we did with stars, we can use classification and actually make some pretty basic classifications that make sense of this huge population of galaxies. So it turns out there are only 3 main types of galaxies that are observed. There are the spiral galaxies, elliptical, and irregular. So a spiral galaxy is like our Milky Way galaxy that we just explored in the last part of this lecture. Spiral galaxies are unique with their spiral arms of stars and gas and dust that wrap around the core or nucleus of the galaxy. Elliptical galaxies are very different. They don't have the spiral structure at all. They're more like just a sort of a swarm of stars. And again, remember this picture here, it just looks like sort of a fuzzy blob. But what we're actually seeing here is the collective starlight from hundreds of billions of suns. And individually, they're just too small and far away to see them. But all together, they kind of make this hazy glow. The third type of galaxy is an irregular galaxy, and this is an example of one, and they don't have any particular shape at all. They are therefore irregular in shape. So we're going to take a look at some of these 3 types of galaxies in more detail in this section, in this part of the lecture. Let's start with the irregular galaxies. Here's a nice sort of a collage of 4 different irregular galaxies that were imaged by the Hubble Space Telescope. And because they're irregular, you can see that they all look very different from each other. It's thought that these irregular galaxies result from collisions or mergers with other galaxies. And this is very evident when you see a picture like this, where 2 galaxies are actually interacting with each other, and that distorts the shape into something that's irregular. We'll talk about galaxy interactions later in this lecture. One other thing about irregular galaxies that's kind of interesting is they often exhibit a very high rate of new star formation. And the reason for this is because these galaxies are the result of interactions with other galaxies. The gas clouds become compressed inside these galaxies, which triggers star formation. So these galaxies are sometimes called starburst galaxies because the new star formation and star birth rate is very high compared to regular galaxies. So how many galaxies are out there in the universe? Well, we don't know for sure, and we don't know the exact number. However, we have a pretty good idea of at least a decent estimate. Using surveys and statistical methods, for example, the Hubble Deep Field image and other surveys of galaxies, including not just in visible light, but in all the wavelengths, including X-ray and infrared, those tell us that there are at least 100 billion galaxies that are visible in our observable part of the universe. And there are certainly more galaxies that exist beyond our limit of vision. And so if the universe is infinite in extent, there may well be an infinite number of galaxies. But at least in the portion of the universe that we can see, we know there are at least 100 billion galaxies. And more recently, this number has been increased quite a bit because they think there may be as many as 10 times this number due to dwarf galaxies that are very difficult to detect. This is here are a couple galaxies that I imaged with my telescope and a digital camera. This is the Whirlpool galaxy here, and this is a galaxy called M81. These are both spiral galaxies, and you can see obviously the spiral arms in both of these galaxies show up very nicely. Here are some Hubble Space Telescope galaxy images, and not surprisingly, these are much more detailed than I could ever dream of doing with my home-built telescope down here on Earth. This is the Whirlpool galaxy, the same one that you saw in the last slide. This is how it looks to the Hubble Space Telescope. This is M104, which is called the Sombrero Galaxy because it looks like the hat. And this is another spiral galaxy here, NGC 4414. And this one is sometimes called the Cigar Galaxy. It is an example of a galaxy that is in the process of interacting with another galaxy. And so that's why it has sort of an irregular, distorted shape. The largest galaxy that we have discovered to date with our telescopes doesn't have a very descriptive name at all. It's a catalog name, IC1101, and it lies at the center of a galaxy cluster called Abell 2029, and it's about 1 billion light years from Earth, so it's not a close neighbor by any means. But this galaxy is absolutely enormous, and you can see it in this photo as this central kind of foggy haze. Here is the core of the galaxy, the bright part here, and you can see it sort of extend diagonally in the image here. Now, one thing to keep in mind is all of these other fuzzy spots in the image here, these are not stars. Those are galaxies that would be similar to our Milky Way in size. So this galaxy is obviously much larger. In fact, it has a diameter of about 6 million light years, which is 50 times larger than our Milky Way in diameter. The mass of this galaxy is estimated to be 2 times 10 to the 15th power suns, which makes it 2,000 times more massive than our Milky Way. And the number of stars in this galaxy is estimated to be at 100 trillion stars. So this is the current record holder for the largest galaxy in the universe, and there are probably certainly larger ones, but we have yet to find them. Let's take a little step back now and introduce a famous American astronomer, Edwin Hubble. You've probably heard of the name Hubble because we've talked about the Hubble Space Telescope, which it is named after the astronomer Edwin Hubble. So he is famous for a couple of things. In 1923, Hubble was the first astronomer to measure the distance to another galaxy. And so interestingly, before Hubble did this, everybody thought that the entire universe was basically existed inside of our Milky Way galaxy. The other galaxies that were seen by telescopes were thought to be part of our Milky Way. They were thought to be either star clusters or just a nebula of gas and dust and stars and so forth. It wasn't until Hubble actually figured out a way to measure distances to these galaxies, and he realized that, wow, our universe is a lot bigger than we previously thought. All of these little faint fuzzy smudges in the telescopes are separate island galaxies, and they're separated by enormous distances. Hubble's other big discovery was in 1929. He discovered the expansion of the universe by plotting galaxy speeds, which they're all speeding away from us, versus their distance from us, and this relationship is known as Hubble's law, which we will now look at more carefully. By the way, these images here, this picture here, was taken up on Palomar Mountain. Not sure when, I would guess probably in the 1940s or 1950s, and Hubble visited there often. So Hubble is famous for the law that's named after him, Hubble's law. It's a powerful method to find the distance to other galaxies. So what Hubble did is he made a plot of the speed that a galaxy is moving away from us versus its distance in millions of light years. All right. Now, how did he measure the speed? Well, he used the Doppler effect to measure the shift of the spectra of the galaxy. And so by doing that, it's sort of an indirect way to figure out how fast galaxies are moving away from us. And Hubble found that it wasn't just a random relationship. He found that in general, the farther away the galaxy is, remember this is distance from us down here in millions of light years, the farther away the galaxy is, the faster it appears to be moving away from us. All right, and so this is going to be a key piece of evidence, actually, for the Big Bang Theory, because what this tells us is the universe is expanding. But we're going to talk about that later in the next chapter on cosmology. But for right now, we can just kind of appreciate that Hubble's law here allowed astronomers to measure distances to other galaxies by measuring how fast they're moving away from us using their shift in their spectra. So without getting into all the details of Hubble's law, because you really won't be asked for that, I will just kind of go over it real briefly here. What he did with this data, each one of these points here represents a different galaxy at a different distance from Earth. And he fit a line, basically, this straight line here through the data. Now, remember from math class, the equation for a line is y equals mx plus b, where m is a slope and b is the y-intercept. So on this graph, the y-axis is the recessional velocity, or v sub r. The x coordinate on this graph, which is the horizontal axis down here, is distance from us, so that's d. And notice the y-intercept, is where this line cuts through the y-axis. Well, it cuts through at 0. There is no y-intercept. So b is just 0. And so the slope here is interpreted to be a constant, which is called Hubble's constant. So what Hubble's law says is that the recessional velocity of a galaxy, meaning how fast a galaxy moves away from us, is equal to the Hubble constant times the distance of the galaxy to us. And basically what this says is the larger the larger d is here, the larger the recessional velocity. And so by working backwards, by measuring v, astronomers can figure out d, the distance to the galaxy. And the Hubble constant, by the way, we'll mention this again in the next chapter on cosmology. The current value is around 70, and it has some weird units here, kilometers per second per megaparsec. So using Hubble's law and other ways to measure galactic distances, we can take a look and see where these galaxies are in the universe in relation to us. So a close galaxy is, again, the Andromeda galaxy, our nearest neighbor. And remember what we mean by close. It's all relative, right? Close is 2 million light years away, okay? And that means, again, the light takes 2 million years to get to us from this galaxy. So, that is again, a mind-boggling distance But remember, this is a close galaxy. So one that might be called far this is actually a cluster of galaxies. So all these yellow fuzzy blobs in this picture, and there are probably several hundred of them in this picture, each one of those is a galaxy, like our Milky Way, with hundreds of billions of stars in it. So this whole cluster of galaxies, called Abell 1689, is approximately 2 billion light years away. So when we see a photo like this taken from a telescope recently, we are looking back in time to what this cluster looked like 2 billion years ago. Now, let's really stretch it out. A galaxy that's really far away is this little fuzzy blob here that's circled. And this galaxy has a catalog name, which is given right here, and it has an estimated distance of 13 billion light years. So we're looking back to the early part of our universe's history. We'll learn in the next chapter that our universe is about 14 billion years old. So we're looking back to a relatively early era of our universe's existence. And, that's why we don't get a really good look here at this galaxy. We're looking back so far and so far away. And interestingly, because the universe is expanding, this galaxy is not 13 billion light years away now. It's actually 29 billion light years away from us, because during the 13 billion years that this light traveled to us, it has been moving away from us. And so it is now 29 billion light years away. Galaxies are usually not in isolation, but they are part of a larger group of galaxies called a cluster. So let's take a look at galaxy clusters. Some galaxy clusters can contain more than 1,000 galaxies. So this is one that I think I've already shown you. This is galaxy cluster Abell 1689. And again, in this picture, every one of these fuzzy blobs that you see is a separate galaxy, like our Milky Way galaxy. And so this cluster certainly contains, I would guess, several hundred galaxies in it. So these are enormous structures, okay? Remember, just one of these galaxies, like this one up here, is like our Milky Way or the Andromeda Galaxy. And so here we have a collection of up to 1,000 galaxies like this. Now, our Milky Way galaxy is part of a relatively small cluster called the Local Group, and it contains around 50 galaxies. And amongst those 50 galaxies, there are really only 3 large major galaxies. The others are small dwarf galaxies. So plotting the sort of the distribution of this cluster, let's put our Milky Way right in the center, all right, since we want to look at everything relative to where we are. The other 2 big galaxies in our local group is the Andromeda Galaxy over here, which you've already seen pictures of, and there's another one over here called M33, or the Triangulum Galaxy, which is also another large spiral galaxy. But other than these 3 galaxies, the rest are all relatively small, minor dwarf galaxies or small elliptical irregular galaxies. We saw in part 1 of this lecture on the Milky Way that in the center of our Milky Way galaxy there is a supermassive black hole. So it turns out that supermassive black holes are found in the centers of most large galaxies. And these black holes, remember, can have several million up to more than 1 billion solar masses. So these are very different black holes than the kind of black hole that forms when a star blows up. And we saw that earlier in the course in the chapter on stars. These are black holes that have a different origin, and we're actually not sure how they originally formed. There's still research and data being collected to try to figure out what is the origin of these supermassive black holes. This is an example here. This is an image of galaxy M106, and it has a supermassive black hole that contains about 40 million solar masses. So remember, what we mean by that is you can think of 40 million suns crammed into a region of space smaller than an atom. It sounds almost unbelievable, right? Or impossible, but this is the strange and mysterious nature of black holes. Here's another example of a supermassive black hole in the giant elliptical galaxy M81. So M81 is an elliptical galaxy, and you're seeing this kind of hazy fog in this picture here. This is the core of the elliptical galaxy here, and this bright spot in the center is near where this black hole sits. This is actually a jet of material that's being shot out of the black hole. Remember that black holes can have these bipolar jets of radiation shooting out from them as material falls into the black hole. So calculations by basically looking at the orbit of stars around this black hole, we can indirectly measure the mass of the black hole, and it was found to be more than 3 billion suns. So again, this is just an astounding and almost mind-boggling concept to think of how you could have 3 billion of our suns crammed into a space tinier than an atom. This is an image, I think I showed you this in the last chapter when we talked about black holes made from stars. So this is the supermassive black hole at the core of galaxy M87. And this particular one is measured to have a mass of 6.5 billion suns. And again, you know, this is just an amazing concept to have that much mass in such a small area. But this image was taken using radio telescopes. This is not a visible light telescope image. It was obtained by connecting several radio telescopes together to form what they call the Event Horizon Telescope, or EHT. And because these telescopes, these radio telescopes, were on different parts of the globe, they were able to take advantage of basically having almost like a very large single radio telescope the size of the Earth to get a very detailed image. And so in this image here, you know, we can see part of the accretion disk glowing here, and the central region here is getting closer and closer to the event horizon of this black hole. Here's another example of a supermassive black hole in the core of galaxy NGC 4261. This image over here is kind of interesting. This is a composite image. The white part of the picture here in the center, the white fuzzy part, is a visible light image taken with a regular telescope in using light, and this is what we would see with our eyes. This looks like some sort of elliptical galaxy here. Now the colored part of the image here is from a radio telescope, and these are jets of radio emission, basically radio waves shot out from the core of this galaxy, and these are called radio lobes over here. And you know, this whole thing is obviously enormous. This whole picture here is around 100,000 light years across. But if we zoom in on the center here, let's see, this is actually taken with the Hubble Space Telescope, we can see the evidence of where this black hole sits, and this is a kind of a cool picture of it as well. And this black hole has a calculated mass of 1.2 billion suns. Here's our last black hole picture, but this one's special because this is the largest black hole that has ever been detected. And so far, this is the record holder for the biggest black hole in the universe as far as we know. And obviously, we're just starting to explore our universe. But this particular supermassive black hole is in the core of a galaxy that has a catalog name, NGC 1277. It has a mass of 17 billion suns. And the event horizon of this black hole, remember, that's sort of like the outer surface of the black hole where you can check in but you can't check out. It has a diameter of 660 astronomical units. Now remember, the distance from the Earth to the Sun is 1 astronomical unit. So the size of this black hole is more than 600 times the distance between the Earth and the Sun. So this is, obviously an enormous black hole, and it has an incredibly large mass of 17 billion suns. One of the interesting things about studying galaxies is to learn that galaxies are very dynamic. They don't just float there peacefully in space. They're always moving, and they're very often interacting with each other. So the galaxies that are inside galaxy clusters are relatively close together, and they often interact. So the interactions include collisions, which is shown here, where two galaxies are actually colliding against each other. Mergers, when later on these two will actually form a single larger galaxy, or cannibalism, where a large galaxy actually just consumes a smaller galaxy. Here's a computer simulation of a galactic collision of two spiral galaxies. Now this computer simulation has been sped up many, many times in order to show what happens over a long period of time. So this whole process that we're seeing in this video clip here would normally take at least 1 billion years, and perhaps much more than that, maybe 5 or even 10 billion years. But what we see are two galaxies approaching each other, and they're approaching each other due to their mutual gravitational attraction. So that means that gravity works over the vast distances of the universe. And because these galaxies are so massive, because they have so many stars inside of them, that they have a large amount of gravity and they attract each other. So as they come together here, you can see that the two galaxies sort of tear each other apart, and the final product is a very disrupted version of the original galaxies. Their original nice spiral arm, form, which is very regular and symmetric, that's completely gone after the galaxies tear into each other. So here's this is another image of two galaxies in the process of colliding and merging together, and you can see they're distorting the shapes of these galaxies. One thing that's kind of interesting here is that the galaxies like this often collide. It's very common. We have pictures of hundreds or maybe thousands of galaxies undergoing mergers and collisions like this. However, when these galaxies collide, the stars inside of the galaxies almost never collide or interfere with each other because of the vast distances between the stars. So this, when we see a picture like this, it doesn't seem possible. It seems like the stars would all be slamming into each other, because remember, each of these galaxies has hundreds of billions of stars. One way to kind of see, though, why the stars don't hit each other is by getting a sense of scale for the separation. So if I were to take a couple of tennis balls and have them first represent galaxies, then I could maybe place the tennis balls about 1 meter apart. And it's easy to imagine these tennis balls hitting each other because, they're only about 1 meter apart or 3 feet apart, something like that. So if we had a cluster of 100 galaxies, or 100 tennis balls all floating around inside of a classroom, you could imagine that every once in a while those tennis balls are going to hit each other, okay? But now let's talk about the individual stars inside these galaxies. So in order to space out the stars with the appropriate scale, let's let our tennis balls now equal a star instead of a galaxy. So what I would have to do is take the tennis balls and separate them by a long distance, because the stars have a lot of space in between them. So if I wanted to represent the distance, the average distance between two stars, I would have to take a tennis ball and put one, let's say, place it on the floor, take another tennis ball and drive 400 miles and place that tennis ball at that city. So like one tennis ball might be in San Diego, the other tennis ball would be in San Francisco. And those are the closest stars that there are, the closest to each other. So you can see how what happens is there's so much empty space between these tennis balls, 400 miles, right? The chances of them hitting each other is practically zero. It's just not going to happen. So when these galaxies come together and collide like this, the stars are basically just passing through each other harmlessly. Our solar system, in other words, wouldn't even know that it was colliding with another galaxy, because the stars stars would just slip past each other because of all of that empty space between the stars. This is a famous pair of interacting galaxies called the mice. You can see how they look like the body of a mouse, either a computer mouse or a live mouse, I guess it doesn't matter, and the tail here. And these tails are called tidal tails. They're stars and gas that were ripped from the galaxy during the collision. And you can see in between the two galaxies, there's a bridge of stars and gas and dust. And this picture, by the way, here looks very much like the computer simulation that I showed you a couple slides ago. And so the computer simulation models, we believe, are very accurate in modeling and predicting the outcome of these collisions of galaxies. Galactic cannibalism is when small galaxies are completely swallowed up by larger galaxies. In fact, our Milky Way is certainly a cannibal in this sense, because there is evidence that it has devoured smaller dwarf galaxies in its past. So this is an image here. It's kind of interesting, taken in the infrared. And what it's showing here, this is the outer edge of the galaxy. And this is a galaxy cluster. You can see other galaxies in this image around it, smaller galaxies. But this big galaxy here, notice what's inside of it. It's got multiple galaxies inside its core. And so these are smaller dwarf type galaxies that were swallowed up by this giant elliptical galaxy. I mentioned earlier when we talked about irregular galaxies that they're often called starburst galaxies, and this is because after galaxies interact and merge together, as is shown in these pictures, the galaxies are disrupted and the gas and dust becomes compressed or disturbed inside of the galaxy, which triggers new star formation to start. So inside of these galaxies, notice there's a lot of blue and pink colors. Well, remember, blue and pink colors indicate new star formation, because the hot young blue stars are basically newborn stars, and the pink regions of glowing gas are the telltale signs of hydrogen emission nebula that are glowing from the excitement of the new stars producing all this ultraviolet radiation. So these are a couple interesting examples here of some starburst irregular galaxies. And our last slide here for our chapter on galaxies is, again, a picture of our Andromeda galaxy. And it turns out that our Milky Way will probably collide with the Andromeda galaxy in a few billion years. Apparently, we're on a collision course. So again, what's going to happen to our Milky Way and Andromeda when they actually collide? Well, the galaxies will certainly look very different after they merge together and collide. They will be distorted in shape and disrupted. We won't have the nice spiral arms anymore, for example. However, the individual stars, remember, in these galaxies will not be affected. So, for example, our solar system will most likely be completely unharmed by the merger with the Andromeda galaxy, because its stars will not collide with our stars during the merger. So that is the end of our discussion on galaxies. We will next move on to the next chapter on cosmology. I'll see you then.